Hey everyone, welcome back to the Deep Dive. We love that you're here, ready to, well, dive deep with us into some really fascinating topics. And today, we're tackling something that, honestly, underpins our entire ability to fight infections.
It really does. We're going to be looking at how scientists actually test whether antimicrobial drugs, the stuff we use to combat infections, can actually do their job effectively.
Yeah, it's like before a doctor can even think about prescribing an antibiotic or researchers can develop new ones, someone's got to figure out in the lab if a drug is even going to stand a chance against these tiny but mighty microbes.
Exactly. So we're going deep into these really essential laboratory techniques, these antimicrobial susceptibility tests, or sometimes they're called microbial
Right,
assays.
so microbial assays. Our mission today, if you choose to accept it, is to really grasp those core principles and walk through some of the key methods that researchers are using to figure out, can this drug really take down a microbe?
Sounds like a plan.
Okay, so let's start with, the big picture. Why is it so crucial to even bother with all this testing?
Well, I mean, imagine trying to fight an enemy you know nothing about. That's what it would be like trying to treat infections without knowing how effective our weapons, the antimicrobials, actually are.
So it's not just some abstract lab exercise. This stuff has real-world implications.
Absolutely. This is the bedrock of how doctors diagnose and treat infections every single day. It guides the choices they make about which drugs to use, what dosages to prescribe, and it's also, I'd say, it's the driving force behind discovering new and even more effective drugs.
Okay, that makes perfect sense. So let's get a bit more specific. When we talk about these microbial assays, what are we really talking about? What's actually happening in those labs?
So basically, there are these really carefully controlled experiments where scientists can directly observe how a drug interacts with a particular microbe. And they're designed to answer two really key questions about an antimicrobial agent. One, how potent is it? Basically, how strong is its killing power? And two, what's its spectrum of activity? Which types of microbes does it actually work against?
So we're figuring out not only if a drug can win a fight, but who it can even pick a fight with, right?
Yeah, exactly. And, in the source material for this deep dive, they highlight several different methods that scientists use. You've got broth dilution, agar dilution, disc diffusion, time kill kinetics, and even bioautography.
Wow, that's a lot of different approaches, but I guess different tools for different jobs, right?
Yeah, I think a good way to think about it is they all provide slightly different windows into how a drug interacts with microbes. Some are great for quickly screening lots of drugs. Others are better for really detailed analysis of how a drug works over time.
Okay, so like different battle scenarios, but all aimed at seeing how a drug performs against a microbe.
Yeah, exactly. Some use liquid environments, others use these gels, and they differ in how the drug is introduced and how you track what happens, over time.
All right, and one term I kept seeing was minimum inhibitory concentration, or MIC. What's so special about this MIC number?
Oh, it's MIC is huge. It basically tells you the lowest concentration of a drug, the smallest amount, that's needed to actually stop a microbe from growing. And doctors need to know this because it helps them figure out the most effective dose, enough to actually fight the infection, but not so much that you start seeing side effects or risk contributing to, antibiotic resistance.
Right, because you don't want to be hitting a fly with a sledgehammer if a fly swatter will do.
Exactly. And actually, a rising MIC over time can be a really important warning sign that a microbe is becoming resistant to a drug.
Oh, so it's like a canary in the coal mine, a way to see if a drug is starting to lose its effectiveness. Okay, fascinating. Now, I noticed the source material also mentioned different kinds of agar diffusion assays, like things like well diffusion and disc diffusion. What's the deal with those?
So those techniques all involve using these petri dishes filled with agar, which is basically this gel-like substance that bacteria can grow on. And then you put the antimicrobial agent directly onto the agar, usually in a specific pattern.
Okay, and then what happens? Do they just, like, duke it out on the Petri dish?
Pretty much. The drug spreads out from wherever you put it, and then you can actually see if it creates these clear zones, these areas where the bacteria can't grow. So the size of those zones tells you how well the drug is working.
So it's like a visual representation of the drug's power, like a microbial force field.
Yeah, I like that. And the different methods, things like wells or plugs or discs, they're just different ways of introducing the drug to the agar, but the basic principle is the same.
So whether we're talking about testing in liquid or on these agar plates, it seems like these methods are really the foundation of how we understand and fight off these microbial infections.
You got it. This is the science behind everything from the antibiotics your doctor prescribes to the development of new drugs, to fight the toughest infections out there.
It's amazing to think about all that happening behind the scenes, all those scientists and those little petri dishes battling it out with microbes.
Yeah, it's really quite remarkable.
Well, this has been an incredibly insightful look at the world of antimicrobial testing. For our listeners, I think the big takeaway here is that there's a whole arsenal of laboratory methods out there, like figuring out the MIC and those agar diffusion techniques that scientists use to evaluate how well antimicrobial agents work against microorganisms.
And it's important to remember that this is a constantly evolving field. The methods we use today might need to adapt and change as microbes themselves evolve and become more resistant to our current drugs.
Which raises a really important question for all of you to ponder. Given how adaptable these microbes are, how do you think those assay methods might need to change in the future to make sure we can keep winning those battles and prevent the rise of, those scary drug-resistant superbugs?
Something to think about.
Definitely food for thought. Thanks for joining us on this deep dive. We'll see you next time.